So far, we've discussed solutions and metal-based alloys and how these alloys are related to solutions. We also discussed about phase diagrams, partial solubility, complete solubility of phase diagrams. We went over some examples, and today we're going to talk about steel and phase diagram of steel. So let's dive in. As I said, steel is really important to us because from the old times till the modern times, we are using steel. I've talked about it in previous videos. Link in the description for those 3 lessons that we did before this one if you want to follow on. So you can follow this course with ease. So let's directly dive into the phase diagram of steel. So that's phase diagram of steel. Iron carbon alloy. On the left side here, we have obviously iron, and on the right side, we have carbon. And this one is increasing with respect to the percentage of added carbon. So from here to there, carbon is increasing, and as you can see, up to 6.67%. This is the region of our interest that we make most of our materials from. And also, if you pay attention, the temperatures are from 210 up to 1500 degrees, also the range of our interest. And we want to see what kind of phases form when we mix carbon with iron. And we want to use the knowledge that we had so far, that we gained so far, and apply it to steel. Okay. So to be able to just to have the same template of following phase diagrams, we first look at the liquid phase and solid phase, liquidus line and solidus line, just to distinguish between liquid phases and solid phases, so we understand where we are in this phase diagram. So first of all, the liquid phase, as you can see, liquid here. So this top region is our liquid phase. If we want to mark the liquidus line, which has a border with the liquid phase itself, that would be all this is our liquidus line all the way, all this our liquidus line, and then going to here, that will be all of this is our liquidus line that has a border. So everything above it with respect to temperature, higher temperature. Here we have temperature, and it's going up. So with respect to temperature, everything above it, it will be at liquid state. So that's our liquidus line. Now we know where it is. And the solidus line should have a border with our solid. And if you look here, we have all solid. Also, this is all solid. So our solidus line is this line going to here, going to here, going to here, going to here. So that will be our solidus line. Therefore, when you define your solidus line, everything below it should be solid. And everything between liquid, in the liquid phase and solid phase, we should have at least a 2-phase or binary phase of at least 1 part liquid and 1 part solid. So for example, if you look at this region that we are talking about, here we have 1 part liquid and 1 part gamma solid, which is on the left side. This is our gamma and this is our liquid. So left and right borders define what's in it, what's within them, what's in between them. And also from here, when you have 6.67% of carbon, you have a phase that is forming like that. So this is the phase that we have on this vertical line, Fe3C, we call cementite. This is a compound, iron carbon compound, which we call cementite. So the right border is actually cementite. The left border is this, which is our liquidus line, the left border. Therefore, it's liquid. So it's a 2-phase liquid, the left border, plus solid, the right border, which is cementite, which is a carbon iron compound. We'll get to there to define it. But that's all the phases that we have. One thing that we should define here, and there are two important points when we want to discuss steel and iron carbon alloy, and those are these points. One is this point, which is also named here as a eutectic point, and the other one is this one as a eutectoid points. What are these points? These are important for us because they really define the kind of phases and properties of alloys that we can get. So everything that happens before them, before these eutectic and eutectoid points, the phases that form are drastically different than those phases and alloys that form beyond these points. So we have one eutectic point and one eutectoid. Eutectic is basically when you have liquid at this point transforming into two solids. So in this case, let's make a general form of it. So in a eutectic point, you get liquid transforming into at least two solids. That's your eutectic point. So it's a minimum point in a phase diagram like that. You see that? It's a minimum point that your liquid directly transforms into two types of solid. In this case, our liquid is transforming into gamma, which is our left border, austenite, and cementite, which is our right border. So we have liquid transforming into solid 1 and solid 2. This is eutectic. Eutectoic is a minimum point in a, again, is a minimum point in a phase diagram that you have solid transforming into two types of solid. So above this point, you have one solid, austenite, gamma here. In this region we are. And when you go down here, then you have this phase, alpha, plus right border, which is cementite. So you have two solids and you have two solids. So in a eutectic point, you have liquid having a phase transition to two types of solid, as you can see here. And eutectoid is about a solid being changed into transforming into at least two phase solids. So we have these two uh, important points on a phase diagram. So for all the alloys that are in composition, so in carbon, iron carbon composition, for all the alloys that come before this point, so eutectic point, for all the alloys with respect to the composition of carbon, that have lower amount of carbon than this eutectic point, so they are in a way below behind this point, they are called hypoeutectic alloys. Hypoeutectic alloys. So for example, the amount of carbon for eutectic point is 4.3%. If an alloy has, let's say, 3%, we call it hypoeutectic alloys. And for all the alloys that come after this eutectic point, we call hypereutectic alloys. So if you have an iron carbon alloy that has 5% of carbon, then we call it an hypereutectic alloy because it has more carbon than 4.3%. Now let's switch to this eutectoid point, which is basically a solid being transformed into two other solids. So in here we have austenite going to ferrite and cementite. So here we have eutectoid. So at this point, everything with the carbon composition lower than 0.76%, we call hypoeutectoid alloy. See that here, hypoeutectoid alloy. For any composition that has less amount of carbon, that's 0.76. And for every alloy that comes after this point that has more carbon than these eutectoid points, that 0.76, for example, 1% carbon, then we call hypereutectoid alloys. So this is a eutectic point. Liquid in equilibrium or changing into two types of solid. Everything lower than that we call hypoeutectic, and everything with a higher carbon composition, that eutectic point, we call hypereutectic. The same goes for eutectoid, that is solid going changing into two other solids. Everything with a lower carbon composition than 0.76 we call hypo, and everything, all the compositions that have more than 0.76 amount of carbon we call hypereutectoid alloys. And they make a lot of difference in terms of phase formation and therefore mechanical properties. I explain how. But first it's important to name them and define them, and then we'll get into more into detail what kind of phases form and how they form, what do they look like under the microscope if you want to predict their formation. So this is about eutectic and eutectoid, and hypereutectic, eutectoid, all these important points. One other thing that we need to define is a limit of what we call steel. So in this diagram, everything, all the alloys that have a composition less than 2.1%, so all the alloys from 0.001 till 2.1% of carbon, we call steel. And any kind of carbon iron alloy that has more carbon composition than 2.1, we call cast iron. So this is the borderline between cast iron, what we call cast iron, and what we call steel. So any carbon iron alloy that has carbon composition lower than 2.1 we call steel. And then we have different kinds of steel. We have hypoeutectoid steel and we have hypereutectoid steel with different compositions. And also when it comes to cast iron, you can have hypoeutectic alloys and hypoeutectoid alloys. But because we are mostly concerned with steel, we will focus on this region on the left side, on all the compositions below 2.1% that makes up steel and different kinds of steel. That's why in some phase diagrams with respect to carbon composition, everything more than 2.1% is cropped out, because they just want to focus on steel, not anything else. Therefore, that's why you see some of the phase diagrams are cropped out. So we also want to focus on the steel part, on the left side of this phase diagram, to see what kind of steel phases will form and how they determine the mechanical and physical property of our steel, so we can change the property of our steel for the application that we want, and we understand why the properties will change. So this is a part of the steel. This is a part of a steel, as you can see, from 0 to 2.5. So the steel part of the phase diagram, and from 400 degrees to 1100 degrees. If you pay attention, here we have gamma austenite. So this is a zoomed in version. And if I go back, this gamma austenite at 1100 degrees, we are below this solidus line that I marked before. We are below that. Therefore, here we have fully solid. So this gamma austenite at 1100 degrees is below the solidus line. Therefore, we have solid. Okay. So we are in purely solid region. That's where we are. Here we have gamma austenite phase, which is a solid. And on the right side, we have gamma plus what I told you is a compound iron carbon compound, which is called cementite. So we have austenite plus cementite in this region. And here we have alpha as alpha steel, which is called ferrite. We have ferrite plus austenite. And here we have a solid solution. As I said, we have a single phase solid solution, which is called ferrite or alpha phase. But we want to know what kind of phases form and how do they look like. Well, you see and kind of an abstract of the phases that are forming. So we want to allocate each of these phases to a certain temperature and composition, so we understand how steel is formed and what is the difference between hypoeutectic steel and hyper sorry, hypo-eutectoid still and hyper-eutectoid still. So here we have a minimum in phase diagram. As I said, we're looking for minimums for eutectic and eutectoid points most of the time. Here we have a minimum that one solid austenite, if we cool it down, changes into this one, alpha plus Fe3C. So ferrite plus cementite. That's our eutectoid. Why? Because gamma is solid, alpha is solid, and cementite is solid. Therefore, that's a eutectoid. If it was liquid instead of a solid, then it was eutectic. But this is our eutectoid points. So this is our eutectoid points. I mark it with E, and all the alloys with carbon compositions less than this amount will be hypo-eutectoid, and the alloys coming after that are hyper-eutectoid. So let's bring our ruler, and I'll make a straight line here. And also bring it over here for another alloy, and let's see what we get. So for this composition, imagine we are at 0.25 here, and here we are at 0.25. So we are at these two carbon compositions, iron with two carbon. So one, we have iron with 0.25% of carbon, and the other one, we have iron with 1.25% of carbon. This one has lower carbon composition than our eutectoid points. Therefore, it's a hypo-eutectoid alloy. And this one with 1.25% of carbon has more carbon than this point. So the carbon at eutectoid point, that's how you know it. So this is the carbon composition of our eutectoid point. Everything with more carbon composition is hyper-eutectoid. Anything with less carbon composition is hypo. So it's hypo and that's hyper. So let's begin at this temperature. At this temperature, as we said, austenite is in solid phase. So at this temperature for a hypo-eutectoid alloy, we are in gamma austenite phase, which is a single phase gamma. It's a solid solution of iron and carbon. So as we said, solutions is just one phase. So it's one phase single solution solid of austenite, which is this one. So it could look like that. It's just a solid phase with gamma austenite, and this is just austenite forming. For a hyper-eutectoid alloy, it also shows that, hey, we are at the austenite phase. So again, look like that, and that will be your austenite. So in that temperature, no matter what the composition is hypo-eutectoid or hyper-eutectoid, they have the same phase at this temperature. Now let's bring the temperature to here. And I think maybe it's best to also make horizontal lines. Good. Then one down. Okay. So when we are cooling down from this point to this point, right, we are at two different phases. At this point, when you are cooling this alloy down, it tells you that you are exiting the single phase austenite or gamma phase into a binary phase of alpha and gamma. So this one should disappear, and you gotta have a new phase that is gamma plus alpha. So in your austenite, which was blue, something else should grow. What is growing? The phase diagram tells you the left border that is alpha, your solid solution, is growing, okay? Now, as you go down, the amount of alpha should increase, and I tell you why it should increase. But you're lowering down the temperature, and the amount of alpha is increasing. So therefore, at this point, it will look like this. At this point, it will look like that. Orange is alpha, and you can see alpha is growing. That's what you see. And I'll tell you later on, after we read that, how to calculate that, how much alpha. When we say alpha is increasing, how much alpha. But anyway, these images are showing you that the alpha is increasing, and then you cool it down even more to this temperature. Well, because you pass the eutectoid line, it tells you that alpha plus gamma should turn into something else when we're coming to this region. And this region, the left border is alpha, which is a solid solution of iron and carbon, single phase. And the right border is cementite again. So you get, in this region, you get left and right border, which is alpha plus cementite. So in this, at this temperature, because you're in this region, you're getting this. And orange is alpha, and blue is cementite. The phase diagram is telling you what you should get. So this is for hypo eutectoid alloys with carbon compositions lower than the eutectic point. Now for hyper, you started with austenite because you were in this region. As you're cooling it down, you're entering a two-phase region. Left border is austenite, right border is cementite. Therefore, you should get gamma plus cementite. Exactly. So this is your austenite, and this is your cementite that is forming. So as you are cooling it down, also looking at this image, it shows you that the amount of cementite, so this was still austenite, and the darker blue is cementite. It tells you that the cementite is also, this is also cementite. It also tells you that your cementite is growing. And then when you, from here, you pull down all the way here, you are passing this line. So gamma plus austenite should turn into alpha plus cementite. Therefore, at this point, you should get this. The orange is alpha again. The dark blue is cementite. So we got all the possible phase formations and how they could look like when you look at them under the microscope in terms of phase fractions and how they shape and arrange themselves for hypoeutectoid and hypereutectoid. I also had an image here that I think it's good to bring it on. This image is for the phase formation exactly at the eutectoid point. So we discussed hypoeutectoid, hypereutectoid, but at the eutectoid point, if you are at the eutectoid, so if you are here and you are starting from here, cooling it down, of course, in here you have only gamma austenite, it will look like either of them. But as you're cooling down from this region to that region, only one phase transformation will occur because this is a unique property of eutectoid point. You see all these phase formations from austenite to what we get here for hypo and also for the hyper, how many phase changes we have. In here, we have at the eutectoid point, we have only one phase transformation from austenite in this region that either look like this or that directly to this, which is again, this one is again alpha plus cementite, just like all the other alpha plus cementite, alpha plus cementite, and this will be also alpha plus cementite. So they all have, no matter the composition, when you are cooling it down, it seems all of them to have alpha ferrite plus cementite, right? So what's the difference? The difference is if you pay close attention in the arrangement of the phases. So for hypo-eutectoid alloy, which is on the left side, look what is the continuous phase. The orange on the left is the continuous phase. See how it's continuous? The continuous phase on the hypoeutectoid alloy is alpha, ferrite. For a hypereutectoid alloy, the continuous phase, now this is the continuous phase. See that? The continuous phase is cementite. It's a different material. What you get for a hypoeutectoid alloy is an alloy that has alpha ferrite as its continuous phase, the orange in the end. And then on the right side, you get an alloy that has cementite, the dark blue, as its continuous phase. They both have alpha and cementite, but their arrangement is very different. And that determines their mechanical property immensely. How? Ferrite is a very ductile and malleable material. Cementite, on the other hand, also the name kind of gives it away. The cementite is very hard and brittle as opposed to ferrite. Ferrite is really soft and malleable, and cementite is really brittle and hard. It's like ceramics, kind of a ceramic-like behavior. But ferrite is like a purely metal behavior. So when you have ferrite as your continuous phase, your material is much more ductile and formable and malleable because you have a soft material as your matrix, as your continuous phase. But for a hypereutectoid alloy, because you have cementite, a ceramic-like material as your continuous phase, as your matrix, that brittle behavior determines the general behavior of your material. Therefore, hypoeutectoid alloys, which have ferrite as their continuous phase, are much softer and malleable, much more ductile as compared to hypereutectoid alloys, which have cementite as their continuous phase. Therefore, it's like they have a ceramic base material, like the general properties is like determined by a ceramic-like material. So they are they are harder and more brittle than hypoeutectoid alloys. And of course, at the eutectic points, you get something like the best of the both worlds. You get something between a hypo and hyper-eutectic alloy with the composition that you see here. So that will be the difference. It's quite a slide, huh? It's a one slide with a lot of information, but when you break it down, then you understand everything. What are different types of steels? So we have low carbon steel, to medium carbon steel, to high carbon steel, and they might have the same kind of phases, but how they arrange themselves, how they orient themselves also, they determine the general mechanical properties of your alloy. One thing very important to note is that these phase diagrams, no matter for what material is, for sugar, for magnesium, for copper and nickel, or for iron and carbon, they have one thing in common, that these phase diagrams are constructed at equilibrium cooling. What do I mean by equilibrium cooling? Is that we derive these phase diagrams by experiment and by cooling down our alloys extremely slowly. So when on these phase diagrams, we are discussing and say, hey, we are going from this point to this point to that point, we are reducing the temperature, cooling down extremely slowly in a controlled environment. So it's not like that we melt our pot and we take it out and we let it cool down in air. No, air cooling is too fast for this kind of phase diagrams because we need to give materials to fully give time to materials to fully form their phases. For these phase transformations, we need time. atoms need time to move and form new phases. So we kind of by slowly cooling them down, we almost give them maybe infinite or more than enough time for those phases to form, and then we cool down a bit more, then a bit more. So we need to pay attention to that the cooling that we are talking about is extremely slow. If you if you cool down your material quickly, this phase diagram will collapse. You cannot use it anymore because you get different phases if your cooling rate is different. Depending how much your cooling rate is with respect to extremely slow cooling, which is these phase diagrams, then you might get different kinds of phases. Okay, so if you want to use this kind of phase diagrams for your application, if you really want to make an alloy and you want to make use of these phase diagrams, make sure that your cooling process is extremely slow. Otherwise, you might be surprised by the phases that you will be getting, right? I'll give you an example. For example, in this one, if you have austenite and you cool it down real fast, you don't get alpha plus cementite right away. It never happens. So first of all, when you're cooling it down that fast, one thing that could happen is that the atoms, because they don't have time to move, it remains kind of like an austenite because you need to give it enough time for the austenite when you're cooling it down to slowly transform. This austenite transforms into alpha plus cementite. Slowly, give it enough time. But if you don't give it enough time, this one will not form. If you cool it down real fast, well, first thing, you would freeze the austenite structure because you're not giving the atoms enough time, to move around and make different phases, make alpha plus cementite. And what else could happen? By the way, we call fast cooling, we call quenching in material engineering. So when you cooling down something fast, we call it quenching. Like in the old times when they make swords, like they were forging the swords when it was hot and they put it in their bucket of water. That's what we call quenching, like cooling it down really fast. So if that austenite phase that I showed you, if you're cooling it down real fast, not only you will freeze kind of the austenite structure because you're not giving the atoms enough time to form ferrite and cementite, you also, because of the thermal tensions, like when you have a hot glass and then you put cold water on it, it might break because of the thermal tensions that you apply to it. Same thing happened to your material. Well, it won't break, but it might change phase because of the tension you apply to it. It could be so much that it changes the structure of your material. And that happens for steel, that happens for austenitic steel, that when you have over here, when you have in these regions, also, when you have it in these regions and you cool it down real fast, these thermal tensions could apply. Other than that, you freeze the austenitic structure, so you're not probably getting this, you would just freeze it. You also make some changes to this austenitic steel, and it changes from FCC austenite that has a crystal that has a unit cell like that to a body-centered tetragonal martensite. So all this tension, this thermal tension that was applied to this kind of steel, it changed the unit cell of the material itself. So this thermal tension made this shape shift in steel, and this shape shift makes your material, well, this is maybe to our advantage, extremely hard. So just by, it's the same composition, it's the same structure, you're just now changing the cooling rate. If you cool down slow, you get a kind of malleable ferrite plus cementite. If you cool down fast, you're most probably freezing the austenite composition and structure, but the thermal tensions are kind of shape-shifting the unit cells within the material from FCC austenite to a body-centered martensite, which is much harder than the austenite itself. So you get a hardened material. But the point is that the cooling rate really affects the phases that you will get. So you can no longer use phase diagrams or only rely on phase diagrams to predict what kind of phases you get. And these are the numbers for steel that paralytic steel, when you do it slowly, when you cool down austenite slowly to get paralytic steel, it has 400 Brinell hardness. And when you cool it down quickly to get martensite, you can achieve 700, almost doubling the hardness of your material just by cooling it fast. This shows how versatile this technique is. So this is not something bad. This is actually gives us more flexibility, more tools to alter the property of a material. We can juggle with these properties and get what we want, right? So the fact that I brought this phase diagram and explained different carbon composition, what kind of alloys they make, especially in terms of the general properties here for hypo and hyper-eutectoid alloys, because these kind of alloys that we make with different composition of carbons, they have a variety of applications depending on the composition of carbon. So quickly, I'm going to the examples. We have categories with respect to the composition of carbon, what kind of steel we are getting. So first category is low carbon steel. Low carbon steel, when you add 0.0 to 0.3% of carbon and you add it to iron and you make steel, then we call it low carbon steel. And that's like the most inexpensive version of steel that is machinable and weldable, but it's compared to other types of steel with higher concentration of carbon, we call it a relatively low strength steel. And the application, as you can see in the image, we use it as reinforcement in concrete, this low carbon steel. Although it doesn't have a lot of strength compared to high carbon composition, but it's very ductile, so it makes your concrete really tough because they can bend and absorb all the energy of the deformation. And also they are used in clippers. The clippers are kind of ductile. You can work it out with your hands. So those are low carbon steel. The higher the composition of carbon, the harder your material gets. So this is the low carbon a version of our steel. We call it low carbon steel. And then we go to medium carbon steel, which is the concentration between 0.3 to 0.7 weight percent of carbon when we add it to it, which we call medium carbon steel, which is a bit more expensive than low carbon steel. It's still machinable, it is weldable, but because the composition of carbon is more than low carbon steel, it's harder and stronger. So with the composition of steel, adding it, it will make it harder and stronger. Why it makes it harder and stronger when you add more carbon? It's because of this. Because as you add more carbon, as you go from left to right, the amount of cementite will increase as compared to ferrite. As I said, cementite is a really hard and brittle and strong material, and ferrite is very soft and malleable material. So as you add more carbon, you get more cementite in your steel. Therefore, it makes it harder and stronger. It's the extreme example is for a hypo and hyper, because hypo has low carbon and hyper has a lot of carbon, and hyperalloys are stronger, and that's because of the composition of carbon we are adding to it. So for medium carbon steel, because they're harder and stronger, we can use uh, we can use them in gears, not really high duty gears, but most of the gears can be made from medium carbon steel. If you want to have a very hard gear, then you can also use high carbon steel. Also, drive shafts of the cars can be made from medium carbon steel. One reason that they usually don't go for high carbon steel for drive shafts is because of the medium carbon steel is more impact resistant. Medium carbon steel has less cementite in it, therefore the less brittle material in it. Therefore, it can absorb more impact energy than a brittle material. So drive shaft is a good example of a medium carbon steel. Um, and the other category is high carbon steel, of course. which we go from 0.7 to 1.7% weight percent of carbon. These kind of high carbon steel are extremely hard and extremely brittle, and they are really difficult to machine, difficult to weld. But once you make it, they are really strong, and we usually use it, as you can see here, for hardened knives. These knives can sometimes cut through metal. Like you can cut aluminum and other metals with this kind of knives, and we can make very hard cutting tools with it that can cut also other hard metals. So from hardened steel, we can make extremely hard toolware that we can use to cut and machine other hard metals with. So they have their own application, and all these low, medium, and high carbon steel, they are made using the same phase diagram. That's how we make it. And the last category, we don't call steel anymore. As I said, according to this phase diagram, anything with the carbon composition beyond 2.1%, we don't call steel anymore. Or 2.4, between 2.4 and 2.1, we don't call steel anymore. We call cast iron, right? So here is cast iron. Somewhere between 1.7, so around the range of 2.1 to 2.4, up to 4% with respect to composition of carbon, we call cast iron. And cast iron, we don't use them for structures, but two main applications are pans. We have these high quality cast iron pans that are much healthier than Teflon. This is a good example of that. They're usually really dark, and also older engine blocks. The high quality engine blocks, of course, they were heavy, but they were made of cast iron. Nowadays, they are usually made of aluminum alloy blocks, but the old days with the higher quality engines, they were made from cast iron blocks, but they are really brittle. So upon impact, they can shatter into pieces. So if you drop your engine or in a mechanic shop, or if you drop your cast iron pan, you would break it. So they don't behave like metals anymore. They behave more like ceramic. Why? Because at high composition of carbon, you get a lot of cementite, and as I said, cementite has ceramic-like behavior. So the more carbon you add, the more ceramic behavior you're introducing to your material. So the cast iron, which has a lot of carbon composition, they will start to behave like ceramics, not metals. So that's all about the basics of steel and phase diagrams and how to identify phases. We have one more session left, and that is quantifying the amount of phases and quantifying the composition. So when we say, for example, here we have alpha, and alpha from this amount increased to this amount, by how much? And also, what is the composition of carbon in alpha? Because we say alpha is a solid solution of carbon and iron. So how much carbon is in alpha? How much iron is in alpha? So we're going to calculate that in the next and final sessions of alloys and phase diagrams. I see you next time. Have a good day.